I'm Mike Davis, and we're starting now the 4th week of our program, believe it or not. And this week, our focus topic is a knot theory, and we're fortunate to have Sergey Gukov from Caltech to lead the week. So we'll have a discussion today. We'll introduce each other. We'll put up a list of problems and discussion topics as we had in previous Mondays.
Hi everyone. So I'm Sergey. So yeah, as Mike said, I'm from Caltech, and I'm delighted to be here. So leading this week. Shall we project people to the board on Zoom, or shall we use the board mostly for summarizing the goals?
Yeah, why don't we? That's right. I mean, that's.
Part of the reason I'm suggesting this because probably we should go around the room, introduce ourselves, say what we're interested in, and as we introduce or Zoom people introduce themselves, we should all see you. So that's part of the motivation to make sure we see you on the screen.
Okay, shall we go around the room here?
Sure. Let's start with you, Mike.
Okay, so I'm Mike Douglas. I'm here at the CMSA. And that's just done many other things.
Okay, so I'm Sergey. I'm from Caltech, and let's say a few words about like what's your connection to knots. So maybe my interest, for instance, is I'm mostly interested in training RL to find rare instances with very disproportionate reward systems. So.
Hi, I'm Pavel Rühle. I'm at Northeastern University. Sergey introduced me to the beautiful topic of knot theory, so I learned all from him. Before that, I was using reinforcement learning for problems in string theory and string complexification.
Oh, and I should add that you guys introduced me to the beautiful topic of this.
I'm Thomas Harding. I recently started at IFI. I've mostly worked at applying machine learning methods to string theory and geometry. I don't know that much knot theory, but I'd be interested to look at that.
Hey everyone, I'm Jim Halverson. I'm at Northeastern and IFI, which is an ANA institute here in Boston. I'm a string theorist also, but I'm interested in knot theory. I guess now we're thinking about the classification problem and properties of representations in the embedding space.
My name is Kevin. I'm a graduate student at Boston College. I work with John Baldwin. I work with knots, mostly I guess knot detection. Figure hormology or quantumology. I don't know anything about machine learning.
Yeah.
Hi, I'm Ali. I'm a graduate at BC. I also work in integral floor theory and symplectic topology. I don't know much about machine learning.
I'm Mark Hughes, and I'm at Brigham Young University. I'm sort of a topologist in background, but got interested in ML and what kind of questions in knot theory ML answers. UMG. Well, I don't know if I can put it that way, but
DRA, I have from Hampshire, mostly applying machine learning methods to study string theory. And I just started learning theory, so I know.
I'm actually a postdoc from the University of Sydney, and I've been involved in a grade group / knot theory project with respect to machine learning, and I'm interested to learn.
Great, thanks. Let's go around to the screen now. We have to call out names, and it's not easy because we can't see the names. It's much silly.
Should we start?
This is the names now, actually.
Yeah, there's the names. Kit, can you hear me?
Yep. Hi, I'm Kit. I'm a PhD student at the University of Oxford, and I've mostly worked on applying machine learning to problems in string compactifications and geometry. So, but interested to hear more about knots.
So Francois?
Yeah, I'm François Charton. I work in Meta. I was there the previous week, but now I'm back in France. I know nothing about knot theory and very little about math, but I'm very interested in applying language model, practically transformers, to solve problems of mathematics. So, yeah,
The volume.
You can't hear me?
Barely.
Yeah, 1 second, we'll turn off the volume.
Yeah, it's on our end, it's not your end.
Is it better now? Okay, do you want me to say it again, or have you heard
Yeah,
the first?
just wait 1 second, we're trying to turn up the volume.
Okay.
Really?
Yeah, sorry. Yeah, okay. So I'm Gergely Berti from Aarhus University in Denmark. I am a geometer, algebraic geometer, and I was there for the first 2 weeks of the program. So I have no previous experience with knots and machine learning, but did some work using transformers and reinforcement learning in geometry and combinatorics. So I'm very much looking forward to this week and learn about these applications.
Great, thanks. Alexander?
Hello. So I'm Alexander Chervov. So now I was trained as a mathematician, but now I'm working in applications of the machine learning to biology. So I'm interested in some applications of the reinforcement learning, and especially on graphs to different problems, maybe mathematical, like find the path on the Kelly graph, as well as some biological. And from the Sergey's talk, I know that there are some relations to the knot theory, and I'm very delighted to hear about more about these things. Thank you.
Thanks. Chris?
Hi, I'm Chris. I'm from Georgia Tech, graduate student, CS, also industry data scientist for a few years. I don't know much about knot theory, but I'm very interested in learning. I'm currently working on LLM reasoning projects here on campus. I was there in previous 2 weeks. We'll be coming back after my project is done at Georgia Tech. So, yep, very interested in learning and perhaps contributing and helping people out.
Okay, thanks. Stan, you're muted, so unmute. Yeah.
Yeah, hi, I'm Stan Sredniak from Duke University. This week I will be interested in knot theory, in particular in knot invariants, and I'm also more broadly interested in knot theory, especially connections to resurgence and high-dimensional knot theory and high-dimensional topology. Yeah.
Thanks. Okay, that's everyone. So if you need the board, we can move this, but we can turn this to the board. But until then, we can do things. It's fine.
Well, I think it's probably good now that we turn the board and go over problems or subtopics. But yeah, I should rotate this one. Right. I think it's also worth mentioning that we have in-house experts who could be quite relevant. So Mike Friedman, I don't know if he's around or will be joining us sometimes. So Ellie Grisby and Catherine Lindsay, so they are also teaching a course here on. So I'll just record that Tuesday, Thursday, 2:30, 3:45. So that's the theory course. So theory of learning. So they're also trained as low-dimensional topologists, and I think their interest quite overlaps with what we'll be doing. So hopefully we'll see some of them. And Adam Wagner, so he's mostly interested in combinatorics and ML, but some problems may be close enough to group theoretic structures that we may see. So there are a couple of people which at least I don't see around yet, but hopefully they'll be somewhere here throughout the week. One idea or one thought was to generate a list of topics that we can discuss. So we have designated discussion slots on Monday, today, Wednesday, and Friday, 1:30. So we can use this time wisely, and also Tuesday, right? So Tuesday, that's 4 to 5:30. So 4 discussions, plus we can have some more schedule activities if need be. So therefore, we can generate kind of problems, topics to discuss, anything that people like to suggest. So obvious categories could be problems in knot theory that we may want to discuss or try to solve using ML. Knot theory, so this means just discussing or introducing people to knot theory and not maybe necessarily in a discussion time doing a lot of ML, but setting up the stage or something that we want to, I don't know, clarify. I personally have already mentioned this to Mike and Fabian, and I'll bring it up a bit later. Some questions from engineering side of things. So this is kind of extreme opposite, and hopefully it will counterbalance theory of deep learning. So this is more like practice of deep learning. And then we can have a whole category of either topics or problems in non-theory plus X. So I think if X is group theory, this could be a whole separate category. There are lots and lots of questions which bring us to group theory. But a couple of subcategories here could be where X is, for example, physics, or X equals number theory, meaning arithmetic or similar structures. So then, in addition, I would add that there is a whole probably group of questions involving formal methods, or for instance, mean and math leads. So when I was teaching a course on knot theory a year ago, I looked at math league. There was absolutely zero on knot theory. I haven't looked recently, but this is something that I don't know how many of us. Yes, please.
There are a few people working on it, including myself.
Oh, fantastic. So is the definition of knot there already?
Not in math yet, but yeah, I have thought about.
By the end of our discussion, you'll put it in there. I'm joking. Yes, well, thank you. That's great that there is at least epsilon start, but now we should, yeah. So that's another thing we can discuss, formal methods and applications. Anyway, of course, these are not meant to be all categories, but just to get the discussion going. In fact, now I want to turn this to either Zoom participants or you guys. So please feel free to make suggestions, and I'll hold back. I have many ideas, but I don't want to populate this. So somebody else should volunteer.
Well, one topic which we spoke about in the second week, and we felt was worth developing, is either an analogous or possibly a directly related problem of the shortest paths in Cayley graphs, especially of infinite discrete groups. And there's some material about this on the Zulip already, but the kind of question that came up, and Jordan Ellenberg spoke. We also have a recording about some of these things. I guess it's another category of related problems that I'll say what the relation is. So we might, for example, look at SL2Z or let's say SL2Z, and then we're going to single out 4 transformations, which are T plus or minus 1, and it's transpose. I don't know if there's a standard notation for it. It's more or less ST. paths. And it's all these A1 inverse, A2 inverse. And then you could draw a Cayley graph where you have the identity and then you have edges for each possible generator out of this set. And it's a classic problem if you're given a group element, which in this case, you could give explicitly as a matrix to find a word or perhaps the shortest word in terms of the generators that reproduces this. And from the graph theory point of view, that's finding the shortest path in the Cayley graph from a given point to the identity. And so in some sense, it's a generalized Rubik's Cube problem. We have the Rubik's Cube. You can think of the group of actions. In general, there's a version of the problem where you think about a group acting on a set, but the simpler version is where you just have to group and you can find your shortest path back. And both Alexander Chervov, who spoke about this the first week, and Jordan and his students looked at the problem of learning through reinforcement learning, how to find these paths. It was a famous paper back in 2018 or so of just more than one, but in particular, the first one that successfully solved the Rubik's Cube by learning, by reinforcement learning, and similar techniques work for this. And so there's obviously an infinite set of related problems, and there are, as I understand, many relations between this and graph theory, but the relation which it struck me in some reading, and not something I've worked on, but reading your paper, Sergey et al. On the Andrews Curtis problem, is that the problem which is basically to try to rewrite a group presentation. So you have some balanced group presentation Rn. And so we have generators, we have relations. Does this equal the attribute group with relations to start the group elements being set to 1? And so if there is an equivalence, it's known that there's some big set of moves that can be used to modify the relations and show the equivalence. But then the question is whether there's a really small set of moves, which are going to come up. You can either multiply by one relation by another relation on one side, say the right, or you can conjugate XA. It's going to say XJ, or XJ. So these generate the same group, but can you only by a sequence of these moves turn something known to be a trivial group into the trivial group? And then the relation is, of course, that these are group operations now acting on the space of group presentation. So this is another example of finding a shortest path now in this generalization of Cayley graph, where the graph is group action on some space. And so this is a problem with, again, I think a range of problems, not a very difficult problem that's to target, but a range of problems where you know the answer, where you know a lot about the answer, up into more difficult problems, intermediate level problems, and a single set of methods that can try to address the problems. And so I think that's a promising direction, field of problems to look at.
Yeah, I would love to have more discussion on this at some point, of course, if we have enough time. I want just maybe, I promise not to interject too much or control the discussion, but maybe I'll make a quick remark that SL2Z, for example, so in many problems in knot theory and topology, the group appears as fundamental group of something. So that's a good way to think about it. That's pi1 of typically knot complement, for instance. So SL2Z essentially is the pi1 for trefoil knot, one of the simplest knots. And the problem that we're discussing here appears in many different incarnations. for instance, this Andrews-Purvis conjecture, it's all nice, but it's basically combinatorial group theory version of a knotting problem, which some of us here in the room worked on. In fact, that's how Jim and Fabian introduced me to the subject in the first place. And this moves, so yeah, so I mean, analogous problem in knot theory would be to take a fundamental group of a complicated knot diagram, and then these basic moves would be essentially some kind of Rademeister moves, implementing Rademeister moves. And we would be asking, okay, bring me very complicated looking presentation of a trivial group. If we know that it's unknot, it should be a trivial group, back to the most standard, most obvious presentation. So that's basically what this does. So all I want to emphasize is kind of this parallel, which is very relevant, of course, to our focus week. But perhaps another version, so there are many versions in knot theory of this problem. So maybe it's worth to have this organized discussion because it's a big sort of area or sub-area. But the variant of this, which is super important, is sliceness or ribbon problems. So determining whether given knot is slice or ribbon, it can be phrased in a similar way as finding paths. So we're talking about path finding, but the impact is quite disproportionate in the sense that there are many, I mean, half of low-dimensional topology would be closed if we manage to have a really good tool that tells us what's ribbon and what's slice. So I'm not really exaggerating. Many problems, including SPC4, slice ribbon conjectures, property R, lots of properties, lots of important problems kind of hinge on this. So Mark Hughes, who is here with us, in fact, is pioneer of applying ML to sliceness. So now I'm putting you on a spot. Do you want to elaborate, suggest problems? So, it's been 10 years, so we should first of all celebrate your work, but also propose new stages.
Yeah, so
It has to come out.
Oh, okay, well, yeah, I think, I mean, I think this sort of shortest path problems shows up a lot in some stuff I've thought about. So I guess you know, you mentioned, you know, we worked for some time sort of trying to sort of construct ML agents that could, you know, produce sort of minimal genus slice surfaces and things like that. We sort of took a braid approach, working entirely in the braid group, and sort of came up with agents that would sort of allow you to sort of hands-on construct a slice surface. And then, of course, with Ciprian and Sergey and Jim and Fabian took a slightly different approach, and I think you guys got much sort of stronger results as far as like the crossing numbers you could handle. But I'm interested, I think, just on what Mike was saying about sort of these shortest path problems. You know, the one that comes to mind is I'm interested in sort of quasi-positivity detection and the band rank of a braid. I think you can phrase questions about like slice ribbonness. You know, if you have it, so this question that I'm interested in, or at least one of the questions I'm interested in, is if I give you a braid, you can always write, you know, you can always write the braid as a product of ardent generators for some, you know, if it's in the braid group Bn+1, you can always sort of write it as a product of ardent generators. And so, you know, the first, you know, one of the sort of the first question you can ask is, well, you know, finding minimal presentations, finding minimal representations of your braid in terms of these ardent generators. And you know, that's an interesting question. I'm also interested in sort of, if I give you a braid beta, then you can always also write it as a product of conjugates of these ardent generators and their inverses. So you can write it as basically ardent generators conjugated by arbitrary braid words, and understanding sort of minimal presentations of your braid with respect to those band generators tells you things about like the minimal genus of a ribbon surface that the braid bounds or the braid closure bounds. And so then that has sort of implications on sliceness. And there's sort of a nice set of moves if I give you two presentations of braids written in terms of these products of conjugates of Artin generators that sort of brings you back to this perspective where there's sort of a simple set of moves. And so very sort of well posed or very sort of well set up for sort of like an RL where you've got a finite set of moves and sort of that you can apply to your braids here. And so so I think it's kind of in line with some of these sort of problems here where you've got sort of a fixed or you've got a sort of an initial representation and you want to sort of change the representation of your object by some set of moves that you have. So I'm interested in thinking about problems like that, but sort of from the braid group perspective.
Is there a relevant data set, or you just generate all the examples synthetically?
You can, I mean, there are censuses of sort of like braids that are, you know, large censuses of braids of sort of up to certain crossing numbers. But you can also generate things sort of synthetically. Though of course, so for example, if your interest is like quasi-positivity detection, then you know, if you synthetically generate a braid, you've got usually you want some indication a priori as to whether it's going to be quasi-positive or not. And so you can try and cook up examples where you know it's going to be quasi-positive, but then, you know, there's questions about when you're generating things specifically to be quasi-positive, are you somehow biasing your data set and the representation? Yeah.
That you can generate lots of things synthetically, but if there are really hard things to compute about them, it's good to have.
Yeah. So there are some some data sets that you can use.
It's described on either Zula or some place that we can access them.
They are like the one that, so there's this Dunfield's, there's a census, right, with I don't know exactly.
You don't have to tell me. The point being that it should be something, either a web page you can point people at, or you should list sites, you know, on the Zula so that people kind of know where the stuff is.
Yeah, I can post that there. So I've worked with some students on sort of this problem, but from like a dynamic programming approach. We've also tried sort of merging RL and dynamic programming. And somehow when you use just RL on its own, it doesn't work very well. But if you sort of use if you sort of combine it with some other techniques, we can do well. I'd be interested to sort of see other sort of non-RL approaches.
Can you say a little more? What are the techniques?
So if you sort of look at the group theory behind this, you can sort of essentially what my one student did is he came up with this templating approach where essentially you solve the problem in the free group first. So there's sort of a way to recursively solve this problem, quasi-positive or minimal band rank problem in the free group. And then using sort of the answer in the free group, it sort of limits the amount of, it sort of constrains the possible solutions in the full braid group. And so then you can kind of limit your search space down in that way somehow. So
is it easy to say what quasi-positive?
Yeah, so quasi-positive, yeah. So that's not too hard to say. So every braid can be written as a product of conjugates of Artin generators or their inverses. So you write down your braid as just some product of Artin generators. That's what we would call a band decomposition. But you can also sort of, so it's sort of like a sigma 1, sigma 2. So this would be sort of an example of a braid just written as a product of Artin generators. But if you notice, this sigma 3 is just conjugated by sigma 2. So you can group this together, and this gives you a length 2 band decomposition. Now, because the central elements here of both of the conjugates in our product structure are positive, then this would be a quasi-positive braid. So a quasi-positive braid is just one that can be written as the conjugate of positive Artin generators.
And implicitly, there are things you cannot be written in there.
Yeah. There are ways that there are certainly braids that are not quasi-positive. There is in sort of low index braid groups. So I think braid index 3 and 4, at least, well, 3, there's an algorithm for detecting whether something is quasi-positive and then ruling out when things aren't quasi-positive. In like 4-strand braids, there are sort of sub cases that have been solved algorithmically, but in general, there's no algorithm for detecting when something is quasi-positive.
People think they're probably some.
Yeah, I mean, I think there should be one. There's sort of you can kind of boil it down to just a group theory question, which if this group theory question is the answer to it is yes, then there is an algorithm. Unfortunately, it wouldn't be a very efficient algorithm. And so sort of, you know, RL or ML hopefully will, you know, might give us quicker ways of doing it than this potential algorithm that that you could cook up would involve sort of indexing sort of finite groups and then sort of brute forcing your way through them. So it's nothing you'd actually want to do in practice. So hopefully there would be ways to sort of clean things up.
So the algorithm with so solve the problem on break group with 3 generators, do you know what the complexity of that algorithm is?
Off the top of my head, it's been a while since I've looked at it. It's due to a rev cob though. So I can look it up. I think he probably mentioned it in the paper. It's not, it should be fairly quick. I think you're essentially just yeah, maybe I shouldn't say too much on it without refreshing, but I think you essentially write it in sort of a Garside normal form. And then you sort of take this part once you've sort of pulled out all these Garside, these deltas, and you sort of pluck out sort of a certain number. And if you can make the braid trivial after doing that, then it somehow has to be quasi-positive. And there's only a finite number of things to check. So I think it should be fairly fast. Although maybe, yeah, I'd have to look at it.
So knot theory and three-dimensional topology, as I understand, something where there really is significant software that is valuable in this context. Would it be worthwhile to have a meeting where somebody just kind of goes through that software and introduces it to people, or is that something of interest to you?
Sure, that's
Snappy, yeah.
It's really good.
Yeah, Snappy is really nice. It's I mean, there's other packages and stuff, but I would say Snappy probably is the.
So people kind of could become familiar with it if they want it, or would it be useful for somebody who really knows it to at least demonstrate?
Actually, this could be another good source or topic for discussion because there are lots of packages. So Snappy is not the only one. So even Snappy could easily take like half an hour to review. But beyond that, there are lots of things, especially, for example, related to Covenant homology computable methods. You guys mentioned Heater floor. So this is not in Snappy, right? So
Heater floor is,
it is not the Heater floor is, but it's only migrating. I mean, there are also dedicated things which are not on Snappy.
Yeah, I think Snappy doesn't do the one.
No, I had a student point out, so it does, I think it does Kavanagh now. I think I had a student, I didn't think it did, but I had a student who sent me a screenshot and because I told him, I'm like, you'll have to go use NotJob or something else to find Kavanagh homology, and he's like, well, Snappy gave
right,
me
but
this.
the point is that there are lots.
Yeah, there are,
So
yeah.
I think it would be good to review. Actually, all
should I put software packages on here?
Yeah, why not? Yeah,
And also the database.
Yeah. Yeah, and
actually, I have a quick question before we move on.
Sure.
So, do you remember off the top of your head, like what are the simplest non-quasi-positive knots, like 7 crossing, whatever? What are they?
Oh, I don't know. Do you guys know the simplest?
Infinite dynamics quasi-positive.
There is
Yeah, off the top of my head, I don't know.
It actually plays a role in physics recently. So this quasi-positivity. So I don't know if it's worth discussing, but
yeah.
What is the role that they play?
Something is easy. It's basically triggers easy definition, easy to define and compute versus hard. So for quasi-positive, there is something which streamlines the whole thing and give an answer. Whereas for non-quasi-positive, it's much harder. So there are some like, I mean, it's based on our work with Chypre and Manolescu, where we try to define 2 variable series associated with quantum groups of generic Q. And if the node is quasi-positive, let's say there is very quick way. It's not quasi-positive.
So I'm, yeah.
One more comment or question. So these sort of phrasing unknotting, or finding a ribbon knot or anything like this as just sort of a graph, and then finding a path in this graph. So of course it's nice to find the shortest path in the graph, but in general sort of we would be happy to find any path.
Yeah, for a lot of problems, yeah.
So exactly. So this was my question. So certainly for the things I did, or we did with Sergey, it was enough to find a path, and so the way we set up the algorithm, it was sort of trained to find the shortest one. But if you look at how, let's say, people solve the Rubik's Cube, they don't solve it with sort of the magic number of 22 moves. Even when they are in speed competitions, they solve it with 100 moves or something, because they have these algorithms to permute edges and so on. And of course, the Sergey in his paper, the recurrence conjecture, he introduced also sort of composite moves that are built out of that, and that probably doesn't give you the shortest move, but it finds a path to the identity. So in the problems you mentioned, is it important that you find the shortest path or the a path?
Yeah, so you in these cases you really do like so maybe I'll just step to the side for a second, then I'll come back. So the question I'm mostly interested in is in finding these minimal length band products that give you the given braid. And the reason that you want minimal length is because that sort of, you can reinterpret things like slice and ribbonness in terms of sort of quasi-positive and band decompositions of your braid, and somehow knowing the shortest length band decomposition then tells you sort of the minimal number of saddle moves you'd need to do to resolve the braid to a surface. So in this case, the reason that I like this so much is because there's a way of sort of phrasing sliceness and ribbonness in terms of band decompositions, and you can kind of boil down slice ribbonness into sort of information that's contained inside these band decompositions. But in those cases, you do want the shortest length ones.
You want shortest representation, but you don't necessarily need to find the shortest.
Well, okay, so you want the shortest length representation, but you don't necessarily, you're right, in the state space when you're sort of trying to convert it to, yeah. So as sort of a product of generators, you do want the shortest one, but you don't necessarily care if it takes the shortest path to convert it from the given one.
I mean, of course, we also want to, when we unknown, we want to find this empty braid word.
Yeah.
To show that it is the unknown. So
yeah.
We also wanted to show this representation in that sense, but we didn't care how we got.
Yeah. So I guess yes. In this case, you don't necessarily care when looking at the number of moves taken to get there. You don't actually care. It's the shortest.
Is there a way of actually confirming it is the shortest one once you've got that, without them doing just a brute force search up to that size?
Well, so the problem is that there's a few problems. So sometimes, yes, you can tell that it's going to be the minimal length one. So for example, if it's quasi-positive, then you know sort of how many quasi-positive generators you're going to need, or how many of these positive conjugates you need. The problem with like brute forcing even here is that you can sort of compute all products of bands. Like you can look at all, say, products of two bands, but the conjugator lengths can be arbitrarily large. And so you can't sort of search the space of all products of two bands, because the things you're conjugating these generators by can be arbitrarily long. So essentially when you're looking at the braid group in terms of these band generators, you're looking at a presentation of your braid group that has infinitely many generators. And so
yeah. How do you confirm that it is the shortest one you've ended up with?
That gets kind of to Mike's question, is that you either have to sort of know a priori for some other invariant, you've computed some invariants or something that work in this case. But in general, if you hand me an arbitrary braid, there's no way to confirm whether it's the shortest length one a priori. There might, you might get lucky and be able to do it in some instances, but yeah.
So depending on what you want to do with it, let's say you want to find the genus of the genus of the slice disk or something.
Yeah.
Well, so if you could find something that the algorithm thinks is the shortest one, and then you could calculate sort of some the tau invariant or something. And
yeah.
So if it hits it, maybe it's not the shortest one, but it's sort of good enough.
Yeah, like if it hits it, then you sort of know it is the shortest one. But if it doesn't hit it, you don't know where in between the correct. Because I mean, if you know the slice genus of the knot given by the closure, then that gives you sort of the target to shoot for. So
it will only hit it even only if you found the shortest. there cannot be a longer representation. I mean, there cannot be a representation that's not the shortest representation, but still gives the minimal.
So there's a question about, so if you fix the braid index, so there's another complicating factor that I didn't mention, and that is that sometimes you have to stabilize the braid enough to get it to a point where the sort of two smallest answers will coincide. So if you sort of take a minimal index braid representation, you may need to stabilize it some finite number of times until you're in a state where the minimal genus band presentation gives you the minimal genus slice surface. So that's also sort of a complicating factor there. Oh yeah.
Way of generating multiple non-short representations.
Do you have a way of generating? No, sorry.
If you have a way of generating multiple non-short representations.
Sure. Yeah, because you can. If I give you a braid, you can just the braid word that you're starting with is a one of these band presentations, and then you can sort of apply random walks in this using this set of moves that you have to sort of complicate it arbitrarily. But yeah.
I mean, just another comment. There was Jordi and Elements on the first week. They were interested in a different problem. They were interested in maximizing the number of points on my grid without even trying with that. So what they did is sort of they made it as that would be added as many points as the algorithm could find, which would be sort of making it as simple as in your case would be making the breakpoint as simple as possible, and then they use the transformer to generate more configurations that are of this type, and then they sort of use these as starting points, trying to whether you can push it more. I don't know whether but you could try to sort of once you have something that's the shortest, that's what's the shortest or the best that the algorithm can do, so the shortest word you can generate more of the same in some sense.
Yeah.
I mean, this was your question.
Yeah.
Without making it longer again.
Yeah.
And then trying to see whether if these still represent the same knot, whether you could then sort of start from one of these equivalent braid words to see whether the algorithm can continue.
Yeah.
Yeah.
Marky, can you explain, like, I'm just trying to detect slice genus from a braid. How's that a pathfinding problem?
If you're just starting with a braid closure and you're looking for
So there's two problems that you mentioned, one detecting quasi-positivity and one's detecting slice genus, right? How exactly is the slice genus detection a pathfinding problem?
Well, you can phrase it so if you start off with a braid word, so in like Sergey, Cyprian, Jim, and Fabian's paper, I mean, you guys didn't necessarily use braids, and you were specifically looking for ribbons, right? But you had sort of in their paper, they sort of starting with a diagram, they sort of picked a starting strand of the diagram, and then sort of from that strand had to decide on sort of sets of moves to sort of basically start a band from a given strand in the diagram, and then weave that band through the knot diagram in an arbitrary way, and then connect it at some point. And then in sort of doing so for them, sort of their moves, the path they were looking for sort of involved deciding where to extend this band. If you want to stick in the braid framework, and this is something that I had some students working on, what we did is we essentially thought of bands as basically being either adding or removing Artin generators from the braid word, because that's essentially adding or removing a half twisted band. And so our bands were sort of always just a single half twist in our diagram, but ultimately it was sort of like rearranging our braid word in such a way so we could find those bands, remove them or add them, and essentially just try and get a diagram of the trivial braid in that way. But do it in such a way, tracking the Euler characteristic all along so that you're sort of trying to minimize the Euler characteristic.
And how would you have data if you're trying to train something?
How would you have data?
Like you need some data that you know or you know exactly the genus.
Well, so you could maybe set it up if you're taking an RL approach, you could set it up in two ways, right? Like one, you could kind of have this sparse reward function where you know the target genus, and you sort of say, if you hit this target genus, then we give you some big reward, right? The other way that you could do it is, and this is the way that we did in the braid setup, is we didn't know the actual answer. So for a lot of our, randomly generated braids, we didn't know what the actual target slice genus was. So what we did is by tracking the Euler characteristic, our reward function, every time you added a crossing or removed a crossing, that's like adding a saddle point in your surface. And so that contributes -1 to the Euler characteristic of the surface you're building. And then every time you remove an unknotted component, that's like capping something off. That's like adding a disk to your surface. And so you get +1. And then we had to build in some like inaction penalties and stuff like that to sort of like make it so that it didn't just like do trivial things all the time. And so for that one, you've got a non-sparse reward, but you don't actually, until you've finished that surface, you get some sort of bound on the slice genus. You don't actually know if it's what you want, but hopefully you've set up your algorithm in such a way that it'll prioritize finding smaller genus slice surfaces, whether or not they're minimal. Now, that being said, we didn't have great success, and it could have been sort of an engineering problem where we just needed to somehow optimize things better and find better hyperparameters and stuff like that. So we weren't able to handle sort of, large braids at all. So whereas I think in there they were able to handle diagrams into the 70, 80 crossings. Is that right?
Yeah, can I add a comment? So Mike mentioned this.
I also think the question was misunderstood.
Oh, was it?
I might have misunderstood, but I think he was asking the question of like, how do you establish ground truth? How do you get, for example, how do you get rid of it in the first place to be able to actually train this stuff on?
Well, so in our setup, we didn't actually know ground truth for most of the generated braids, but the idea was to find to minimize the paths we found.
So you didn't have a data set where it's just like this braid is what?
Well, you up to a certain number of crossings you do, but
yeah. So what Mike said previously, the thing that sort of led to the breakthrough in the Rubik's Cube was to do something that's called curriculum learning. So what you do is you start essentially with the solved Rubik's Cube and you turn one edge or so. So you do one step and you solve it. And then the RL agent can actually figure out what the rules of the game or what the goal of the game is. So if you have a generator that you can use to generate the instances of the problem, and you can sort of start with the simplest ones where you just do one step and you already solve it. The algorithm learns from that, and then you show it sort of consecutively more and more complicated things. So what we did in the problem with their game for the unknotting, we just started with the unknot, and we sort of destabilized ones, or we twisted ones, and then we figured out how to solve this, and then we made it more complicated. And for the ribbon knots, we found two different ways of generating ribbon knots, meaning we knew that they were bound with the genus 0, the disk. And that also there, so we started with the simplest ones, and then we made it consecutively harder. And in this way, the algorithm learned, and so it's crucial for success in boss part.
Yeah, we
also then another thing that helps us to do repetition. But once they solved it, we let it solve it more than once. So tricks like this. And
what is this thing called where you go backwards? Like you start with a thing like the mana, and then you go backwards.
Curriculum learning.
Curriculum.
But I think that is basically answers or brings Mike's point back that knot theory is one area where it's very easy to generate a lot of synthetic data. And at least for us, this was crucial. And my understanding is that the market was not maybe as, of course you did, but in a very different setting where we were trying to build slice ribbon kind of pathfinder, whereas Mark's goal is to find genus actually. So even if it's not 0, so we were in sort of different domains. Our focus was genus 0 is crucial. For Mark, I think you would care that even if it's not 0, but 2, then that's still good enough.
Yeah.
My comment was just if you had something there, so if you knew this was, so the size genus was 2 for this case. So if you had like a simple presentation of the knot with size genus 2, you could also try to sort of obscure slightly away from that and make it sort of harder. Build up more and more difficult examples if you know where to start. So if you have these types of generators, it's actually, I think, better than just use a database where you just throw at it tons of examples. If you have a good measure of hardness, of making things more and more difficult, it's good to start with the simplest cases and then have your own generated, which makes it more difficult of these starting points.
I have a question about your slice prevent paper. Have you tried your algorithm on these potential counterexamples of a slice prevent condition, like the T1 cable of the figure 8 and the higher cables of?
Yes, we tried the GST examples.
Uh-huh.
Do you want to? So yeah, we tried the Gomshalm and Thompson examples. So there are so it's an infinite set of proposed counterexamples, and it's known that I think the first two in this family are known to not work, to be not be counterexamples in this family. And we tried it on this, but it didn't succeed.
Oh, it doesn't.
So these are, I think, the simplest one is 17, and then the other one is 35 crossings.
The first one is like 47 crossing, but that's out. I mean, someone proved it's
Yeah,
not.
first, not known, I think, 40 something, almost 50 crossings.
Yeah.
Yeah.
That's the one that is still unknown.
Yeah. So, but I think there are two known. I think the simplest example you can construct in the GST family was on like 17 or something, and then 34 and then 49 or whatever. So we tried these three, but it didn't also for the ones that are known to not be counterexamples, the algorithm also didn't find something. So it should have, in this case, it should have succeeded and it didn't. The failure rate for these knots is 10% or something. I mean, it all depends on how long you run the algorithm.
Yeah.
Yeah, so maybe one should also mention that there are, of course, also a smaller number of crossings, interesting examples whose slice status is not known, even around 20.
Yeah.
And what's curious to me personally is that we managed to, I mean, the solver solves, I don't know, 90-something% in the range of under, I don't know, 40 crossings, but mathematically interesting examples fall into this small percentage which it cannot solve.
Yeah, just because you. I mean, the famous one is the convex nut, and for that you need like.
But the only verified slices you cannot disprove. So of course, the convex nut was running indefinitely.
Yeah, that's the point. For the convex nut, you need to do this magic to prove it's not slice.
Yeah, but the algorithm can only prove slices, it cannot disprove such. So it only looks for the path to the identity. If there's no path to the identity, then it keeps running in the graph.
And have you thought about doing these kinds of things for like Kirby moves between three manifolds instead of for surfaces of?
Yeah, I think Kirby moves or Kirby diagrams of four manifolds would be very useful. I don't know. I mean,
because there is like this problem of computing tensor jury numbers of three manifolds, and basically the only three manifolds for which we know the tensor jury number are connected sums of the Poincare homology sphere, and that's it. We don't know that definitely. I mean, there are guesses like there are certain manifolds that are like surgeries on links with 2 or 3 components, and people they can't be less than that, but there is no way to prove it. And the connected sum of Poincare homology sphere was proved recently, like a year ago, and you need like quivariant instantaneous theory to prove it. It's not easy. So that is
So is the problem what project you're proposing?
Doing this kind of RL on Kirby moves and finding the surgery number of three manifolds.
Yeah, and
number of link the minimal number of link components you need to construct a three manifold. So basically, every three manifold is result of surgery on a link in the tree space. The dense surgery number is the number of the components in that link, the minimal number of components in that link, and there are like 2 moves between any 2 diagrams. So. Which are very similar to band. I mean, one of them is essentially band move, and one of them is just adding an unknot with plus or minus.
But I think that's a little more complicated. So I have a couple of students working on this, and we do it in stages. So our first stage was to develop a product which is better than KLO. So we're already there. So KLO is baggy, clumsy, and so on. So likely we have outperformed that. But putting RL on top of it is going to be pretty hard. So much of what we're discussing is, I would say, prerequisite. So we should solve, for example, genus finder, sliceness, or even this pathfinder before we get to it. Why? Because for four-manifolds, Kirby diagrams have 1 handles and 2 handles, and everything is also labeled, right, by the number. So this is actually much more complicated setup than it can.
Oh yeah.
So even a three-manifold version is still much more complicated. Something which I think comparison-wise is similar in terms of complexity of throwing a relative or machine learning is just the small world of quantum manifolds. So we kind of make our universe a little easier, but yes, we do allow other number decorations and other things. So there was work of Pavel Putrov and his student. So maybe we can put that on the paper, but and they managed to get roughly to the same range of a 20 graph of size, I don't know, 50 or so. So again, with small resources, not like hundreds of H100s, but reasonably small, we get into a range of roughly 100 clusters. But only in the plumbed context, because in general, it's going to be super hard. At least, hopefully we'll get there in 5 years, but I think now for us, for this week, I would mention that's a little too early. It's a good question.
As long as the reference you just mentioned.
Oh, this was from was like a year or two ago? Yeah.
Putrov and somebody that they did Kirby move, find their
or plumbed.
And I'll be happy to start Kalo at some point. So that maybe Kalo.
I don't know. I guess that was probably supposed to go underneath the heading, right? Okay.
Yeah, very enough.
I don't know if it's okay. I don't know if we want to have more discussion. There's a couple other sort of tracks. So I think like the slice ribbonness, there's had some attention there. One area that I think I'm interested in that is kind of on a little different track is sort of, I'm interested in sort of understanding how invariants, what sort of shared information invariants carry. And so one way to sort of try to tackle that would be or one way to sort of, I don't know if this is even the most direct approach, but one thing that I'm interested in doing is looking at sort of translation problems between sets of invariants. So for example, if I give you the Jones polynomial or not, what part of or how much information can you sort of recover of the Alexander polynomial or say the Key-Gardner Floor homology, things like that. And so one way you could try and do that is just sort of take try and just take techniques from machine translation and sort of take one invariant or set of invariants and see how well you can recreate another set of invariants. And so we've done that from sort of a supervised learning approach, from sort of a simple approach of, hey, if I give you these invariants, how well can you predict other invariants? But I think it would be for sort of more complicated things like, say, polynomial invariants or homological invariants, can you sort of, take a transformer that takes as input some sequential input and can it sort of output another polynomial invariant or homological invariant? And then sort of to the degree to which you can do that, you can then sort of try and tease out what's the shared information and where, when it is failing, what is it getting right? What is it not getting right? And what does that tell you about sort of what information is contained in the two?
So that's exactly the kind of problem that Francois set up. He has transformer models and set up exactly for that type of problem.
Okay.
And either offline or I don't know. Francois, are you there?
Yeah, I'm there.
Do you want to comment a bit on that or?
So the int-to-int, right?
Yes.
Yeah, so basically on my, I started developing something because I've noticed in the previous weeks that many of the problems that exist that are discussed here can be described as you have a sequence of integers and you want to translate it into another sequence of integers. How they are related is a problem-specific question. So I have the minimal code for a transformer to do that. It's on a repo, so I'm f-charton on GitHub, and it's on a repo called int-to-int for integer to integer.
Okay.
And so if you want to try it, some people in number theory tried it last week. I can answer any question you have, but it's a good minimal code for transformers if you want to try to do one of these translation end-to-end. So basically you've got to supply training data, test data, and there you go.
Okay,
It's F minus.
okay. That's an O, right?
Well, maybe we can ask Francois to post it on the Zoom, right? Just,
Yes, I'm going to do exactly this as soon as
Yeah,
this.
thank you so much.
This
Maybe in the Not
conversation
Theory
is
channel.
finished, and
So,
I'll open something in Zulip and give the explanation of where to get it and what it's meant for.
okay, fantastic. Thank you.
Francois, we started applying it to a knot theory problem right after your talk last week. It's a fantastic package. Thank you. We don't know if it's yet, but it's like,
I'm happy to see people trying it.
It's wonderful to use, and the code is clear and readable, and
It's this problem of where we try to where we give it essentially different Jones polynomials, and then we try to reconstruct.
Oh, I see. Yeah.
Okay, we're trying to find some. So the goal is to train this and then do some contrastive learning and so on to find something that has Jones polynomial one, but it's not yet.
Also direct classification.
Actually, to be very clear with it, you could use it with non-integer data, because practically, if it's only processing your data, you have only one solution, so you don't need a verifier. It's either the correct solution or not. You're training on something end to end. The data could be pretty much anything. You could use it on graphs, you could use it on matrices, you could use it on group data. So long you have a way to tokenize it and generate data, tokenized data, the model will take care of it. So just saying this because sometimes your data is not naturally integer. It's not really a problem.
I mean, tokenizing and polynomial is straightforward, of course. I mean, they have one variable polynomial.
Yep.
It's good. That's good. I've been struggling with some transformer architectures myself, so this might be easier to plug into some.
Yeah, that's pretty much the point. The thing is that if you start developing your own transformer and choosing the architecture, etc., you won't be doing math for a fairly long time.
Yes. No, that's what I've learned. No, that's great.
And it has the right size. So for source model, it has the right size to put it. So we could even start running it in CPU, but it runs on any GPU. You don't use like an A100 or so. You can just put it on any GPU that it run overnight.
Yeah.
Get it installed.
Oh, nice.
Great. So it's sort of just about the right size for academics to run.
Okay.
Yeah. Typically, you're at a few hundred megabytes of video memory. So anything with 2 or 4 or 8 gigabytes will run. The thing is that if you want to do anything serious with it, at one moment you need to have an access to a cluster, not with big GPUs, but with many GPUs, because you really make a difference when you start sweeping for different hyperparameters, when you start looking at many different seeds on the same problem to start to get some statistical vision of how good the machine is.
So, and what's the range of like the dictionary? Like, I mean, just to get an idea for resources, like how big of a dictionary?
So
will it run with these?
the vocabulary, practically for a transformer, it depends on the size of the transformer, but a good idea is that the vocabulary size. So English is like 50K tokens. You don't want to go over there, or you'll need an inordinate amount of data in order to learn the vocabulary. A vocabulary of like 2, 3, or 10 is probably too small because you'll get long sequences, and this won't be practical. So I like to, when I tokenize integers, typically I like to make them base 1000 or something like that. So basically you got a vocabulary of 1000 plus a few. And this is typically the kind of thing that the machine learns well.
Okay.
But it's very problem dependent. If you have a graph, typically your vocabulary, if you want to encode, the edges as in node, out node, the vocabulary is just the number of nodes. And there's very few ways of making it a little more complicated.
I have a question about this. What about matrices? If you want to encode a sequence of matrices for it, is it the same as integers? You need 1,000.
So if you have matrices, the problem you have is how you encode them. So if you have matrices of integers, you can consider that an n square matrix is just n square integers. If you have small integers that can fit onto, say, 1 or maybe 2 tokens, then you've got 2 or 1 or 2 n square elements in the sequence. The problem won't be your vocabulary here. It will be the length of the sequence. Basically, this kind of architecture works well if you have up to a few hundred tokens. At 1,000, it's beginning to be too big. I mean, it will train, but it will take a very, very long time and be very impractical. So if you're working with matrices, if they are small dense matrices, they better not be too large. Or then if you could encode, several elements onto one single token, so several matrix entries over one single token, which takes some work, but might help. And you might run into trouble on tokenization at this point. But this is a point, if you really have this problem, I'm very happy to discuss and give you a couple of ideas on what should be done.
Okay, thank you. Very nice. I've been up here longer than I'm comfortable with. So anyone else has any?
Just since you talked about the slice-driven conjecture, sub-problem of slice-driven conjecture is about finding ribbon disks of the unknot. That's a new Kirby. That's in the new Kirby list actually, which is basically the conjecture is every ribbon disk of the unknot is just a disk in R3 pushed out.
Yeah.
And it's just, you have a bunch of unlinks and you have a bunch of bands between them. And if you end up with the unknot, you can open up all the bands. I'm not sure if you can apply reinforcement learning to such a problem, but that's might be easier than finding ribbon surfaces for complicated knot. This is just about having an unlink and n component unlink and n-1 band.
Yeah, so maybe you could start off with an n component unlink, n-1 bands, and then try to like sort of add, ribbon intersections, like move the band across a strand of a unlink to sort of complexify your diagram in such a way that you still retain the unknot, but somehow get a disk that has unremovable immersed singularity, something like that.
Yeah.
Yeah, I mean, that seems like a problem you definitely could raise, I think, in terms of RL, because you can start off with just your n-1 bands, you start off really from a fixed configuration, and can you complexify the configuration?
Finding your bands is more complicated.
I guess the problem with that would be, because you'd have to then be able to make sure that, you'd have to be able to recognize that you've still kept the unknot, right?
Yeah.
That you haven't broken
That
it off.
you can use floor theory or.
Oh yeah, I guess you can use configure floor and see if it detects the unknot, or conjecturally, Kavanagh. Or sorry, not. I was saying Jones, but yeah, Kavanagh would as well. Yeah.
Yeah.
But then also recognizing when these immersed singularities can't be removed might be a challenge, but.
And there are like certain conjectures and stuff about this.
Okay.
It's about like how these bands intersect each other, and there's like some sort of intersection. It's makes it unremovable.
Okay.
Yeah.
Cool. Maybe a broad discussion that might be interesting to me at least is I've done a lot, like I've often, because I think about surfaces and braided surfaces. I think it's a natural way to phrase a lot of the questions, or easy, and especially because braid closures give you sort of a sequential way to represent a knot just as a sequence of integers. It's very natural to sort of try to do ML using that. But it seems like there's lots of other ways you can encode knots, Gauss codes, DT codes. Just diagrammatically using matrices, things like that. But somehow it seems like not all of these techniques are created equal, and somehow the algorithms learn better with some and not as well with others. And so it seems like from a practical standpoint, talking about sort of what representations of knots work well and what do not for given applications. But then also from maybe more of a theoretical standpoint, and I don't even know a good way to sort of maybe phrase this question, but it seems like a lot of times we represent with sequences of integers with some properties, but you might be interested in some invariants, and somehow if you were to plot a point cloud of all the knots you have and somehow color them by invariance, you don't get a very continuous view of this point distribution. And so, and you can talk about, there are certain invariants for which, you can sort of change the invariant value arbitrarily poorly or arbitrarily. So given a knot with a certain invariant value, there are examples of where you can sort of change a single crossing and that invariant value shifts by some, arbitrarily high amount. And so I think it'd be interesting to sort of, from a practical standpoint, talk about which representations seem to work well for which applications. But just from a sort of a more theoretical standpoint, like what are the natural ways to represent knots, and is there a way that ML can help us learn sort of ways to represent knots that somehow respect the topology or the invariance that we're interested in?
One thing that comes to mind, grid diagrams.
Yeah, grid. We've tried grid diagrams, and we've done I've done a little bit of RL on grid diagrams, and they seem to work okay for sort of unknotting problems. Yeah.
So I gave a problem that's very similar to this to a student. So there was a paper where they sort of was saying that in some cases, provably, or at least conjecturally, it would be the best thing to do would be to represent the knot as a curve in 3 dimensions.
Yeah.
Curve, and then they said, for example, if you want to find whether the simplest example, whether two knots are linked or something. So you conjecturally try to prove that it's very sensible that you need to look at all the crossings in order to say, okay, these two knots are linked. And then if you project, sort of, if you have this 3-dimensional knot, you project it, you get, I don't know, like n squared crossings or so if you have m strands in there. But in 3 dimensions, you can solve this actually in n instead of n squared. So there's this paper where they call this a 3D saving or something. So there exists a better algorithm actually that will detect this, but the question is, of course, will your machine learning algorithms sort of pick up on this? So the question, first of all, yes, so theoretically you can do it better, and then also the question is practically, actually your machine learning algorithm picks up on this. And so that's a project I had with the student to look at.
We were also discussing this, continuing a bit upstairs before we came. There is a 3D algorithm which we don't think works, but could simplify a knot that is basically a gradient flow. There's this kind of function that you integrate 2 points, periods of points around the loop. You integrate 1 over a distance squared roughly, and then the gradient flow definitely simplifies the knot. And if you take relatively simple knots, they'll turn into the round circle. And so a goal that we had already, this was also in our agreement worked on many years ago. And so one of our goals is that conceivably that simplifies every knot, but one kind of is suspicious, and perhaps there are other critical points that is functional. It doesn't simplify to the unknot, but then it does simplify to some sort of canonical form.
Okay.
So maybe that's helpful in this context of what's the right representation.
Yeah.
Another related question, which is that in this, the problems I was talking about, of course, matrix group, you got the matrix. And so for braid groups, how valuable is it to take explicit braid group representations and say, we're really going to look with that? Those matrices, is that something people often do?
Well, there are like faithful representations of the braid group that you could certainly look at, and that's one approach that I've had some students taking, where instead of representing it as a sequence of integers, represent it as the Lawrence-Cramer representation or something like that. And so we haven't gotten any really results on how well that works, but yeah, going from braids to sort of matrix representations is one thing that would be worth trying.
Maybe there would be a good discussion to, as you said, systematically consider the representation as the task.
Yeah.
Could either make the project a you asked about questions and that's certainly one of the questions of representation influence the learning, and then here's a domain where you know a lot about it. Representations, problems.
Maybe it's worth saying it's something that Fabian and I have been working on for a while. There's the question of like the representations that humans have come up with, but we're sort of we've been trying, and we have some results on it. Hopefully the paper comes out this fall. But we're trying to also learn embedding space representations directly, where knots of the same class are clustering together and knots of different classes are repelling. And so I mean, there's these questions of these human derived representations, which you just listed like way more than I know. But there's just a question of whether there's a better one that you might be able to learn directly. And then if you had such embedding of not classes, and then you started that as your place for your ML problem, where you pre-train some neural network to learn some embedding, can you do better with one of these representations? It also has the advantage that it's like a fundamental question.
And then that also segues into this idea of the foundation model, where you have one model that's supposed to predict everything.
And that was sort of something I was sort of on the learning those representations. Like we played around a little bit with like variational autoencoders and like trying to like and I think another like if you're able to learn better representations, I think one of the goals of us sort of trying these variational autoencoders and other things is that from once you learn some like natural latent representation of your knot space, you can then try to sample from it to sort of obtain knots with certain properties that are desirable. So I think like learning these latent learning these representations is a very, very sort of interesting thing.
This is one part of the discussion that I think is sort of missing to this point. We haven't really said the phrase generative models.
Yeah, generative models.
VAEs, and maybe I'll invite you to say something about generative models. Have you got the conditions working? Because that's the kind of the thing that you
Done like what?
You want to be able to sample from a conditional probability
Yes.
distribution on knots based on properties that you care about.
Yeah, and we haven't gotten that working. So this is kind of a broad class of problems. And generative. This is why I typically use slides. Because I don't know how to spell words like generative when I'm not. So I think there's a few approaches to generative learning, and the like the goal would be like counterexample generation, like like Jones knot conjecture. Can you find a non-trivial knot with trivial Jones polynomial? And so there's a few approaches to these types of things. Like one might be, can I use reinforcement learning to say start with a knot with some fixed property, and I want it to then, say it's a knot with it's a non-trivial knot. Can I sort of let's use the Jones knot conjecture just as like a basic example, but I think there's lots of places you could do this. Starting with a diagram of a non-trivial knot, are there moves that I can do that sort of somehow changes some measure of complexity in the Jones polynomial that I can then sort of step by step modify this knot to end up with a non-trivial knot with trivial Jones polynomial. So you could try and do like RL to sort of generate answers. You could also try and do things like conditional generative adversarial networks, where you're able to sort of put in some sort of input invariant that you're targeting, and then sort of have the GAN sort of produce something that matches that input invariance. You could also,
sorry, for the generative one that you said, if you want to keep like certain properties of your knot fixed, let's say Taggart homology or Copanov homology, these types of invariants, there's also mutation that you can do. Not just the surface as sphere mutation, you can do higher genus surface mutation.
Yeah, so that would be like one natural sort of set of moves is like find mutations that you can do that change the diagram. So that'd be like one for that example for sure.
So I actually have a question / proposal. So we listed lots of problems, but I think not presentations or representations is kind of easiest and prerequisite, especially I think it's more visuals or background. So why don't we try to schedule first discussion or outside of normal hours discussion on not representations, and probably you can easily give prepared or unprepared version of a talk, and I think it would be useful to have it back to back what you guys were doing. Even though this work isn't published, you already gave some talks on this, right? Or just mentioned that. So it's useful to have it sort of back to back. So can we reserve a slot? I don't know if this afternoon or tomorrow morning is good, but what do you guys think?
Sure. I'm also, I would also be happy to show what I did with the student about the different representations.
I'd be interested to.
So I know we have a small seminar room, right? That's available to us over there. So what would be the best time? After lunch today, tomorrow morning? What do you think?
I can't do it Tuesday afternoon because I'm teaching. Other than that, I Good.
But Monday afternoon works.
I'm here Monday and Wednesday this week, maybe also part of Thursday.
Well, then how about Monday afternoon?
That is
This
the
afternoon.
That's right. Just checking that people are awake.
So would you be interested in, like, did you say you had a student that did a bunch of different?
Yeah, I mean, I have a slide or two on that, which, you know, I mean, now I haven't prepared anything.
But that's on the back side.
I mean, yeah.
And you probably have, I mean, I've seen your talks on this, you probably have slides, right?
Yeah, I could find some, yeah.
So how about this afternoon, like, I don't know, what's good time?
Yeah, two.
2 o'clock.
2:30.
2 o'clock?
Okay. That gives you like plenty of time.
So,
one more, sorry, are we talking schedule now or still science?
Well,
I still think we haven't said enough about generative models, but.
yeah, so yeah, so I guess all I would say on generative models is you know, you can do it from an RL approach. There are architectures like, I mean, you know, GANs or variational autoencoders have been things I've been interested in. Transformers you could also try just for some of these generative things.
Another thing you could do, which is like a diffusion model, is just
Yeah.
running these flow backwards. You have a trajectory in 3 dimensions and you start adding noise to it and you try to direct it to favor certain invariants or computable properties.
Yeah, there are questions you could set up for, and I'm thinking again to like ribbon knots and things like that, where you could sort of directly have the neural network learn the surface, not as a discrete sequence of moves, but as like a map from the disk to you know, to the surface or something. So that actually gives you the embedding. So I think there's lots of sort of generative approaches, and I haven't really had any success. I've tinkered with a few of them, but
I think most of the generative models, maybe not the gradient ones that are being discussed here, are ones where you like bake in a lot of information, which has the power that like it can constrain your problem in ways that can be useful. But it also means that you might be constraining the neural network more than is perhaps useful if you really want to let it learn. So like something kind of orthogonal to this is this variational inference stuff that people do, where you have some neural network that, you know, you might pre-train to just give like a uniform prior on braid words, but then you want to approximate some Bayesian posterior where you condition it on some property that you care about. But the nice thing is in a lot of these knot theory settings with these pre-coded packages like Snappy or one of the other ones, there's like really good verifiers. So even if this thing is like totally stupid to begin with, it might be that it completely starts learning to generate samples that are more likely to be sliced, et cetera, et cetera. And I guess I'm emphasizing this point about the variational inference because it's a little bit orthogonal to the types of things where you use RL and you bake in a lot of math. That has its pros, but it might also be nice to sort of just like cast off the chains and see what the neural network can learn. And
yeah.
I mean, these sorts of variational techniques would be almost assuming nothing from the get-go, and then it would be using sort of in a Bayesian sense, it would be using the data of the generated stuff to sequentially get better. So anyways, just wanted to mention that's something that people are doing more and more in generative modeling, is approximating these Bayesian posteriors, where in this case, you'd have some prior on knots, and then you'd have some condition you want to impose. Yeah, but.
well,
Before we go up, let's, are we going to try to?
Yeah, sorry, I didn't.
Summarize.
I didn't.
Yeah, so maybe one suggestion was that whoever proposed the problem or suggestion will write something included. That's how it works on plastics. I actually have 2 more quick questions. I won't keep us much longer for lunch. So one question I have is, I don't know if we have enough critical mass, but I think it would be useful. Would you mind maybe also later in the week summarizing for us what's done for knot theory and Nutley?
Not right now, it's almost nothing.
Well, then it should be short and easy. But maybe you can also tell us a little bit of what you're trying to do with this, and I'm sure there will be some discussion, even if it's like 45 minutes total. I think it would be of value. And I had a request, which I don't know if it's feasible or not. I already mentioned this to Mike and Fabian, that I'm interested in engineering questions, something which is like beyond basic Slurm introduction, kind of intermediate level Slurm or resource management. So I don't know if any of you or someone around here would be willing to give a quick tutorial on this.
I don't know much beyond Slurm, so I can't.
What's the beyond
resource management for use of clusters and.
So you want more than stuff.
Well, what I mean is beyond basic stuff.
So the big transition and Francois was making the point was between training a model on one GPU and training a model on multiple GPUs.
Yeah, but training, excuse me, but training on a couple of GPU is basically why you use Slurm, right? So you have
Right,
Slurm, you have.
Yeah, my question is if it's a huge cluster, not just a couple of GPUs. If it's really large and usual ways of doing it will totally crush everything. So it's basically a complete, it's a different, yeah.
So I can share with, if you have Slurm, I can share with you the code I use and explain to you how to use it in end-to-end fashion. I have no problem with that.
Maybe that will work.
Yeah.
So then two practical questions, at least these two things. Can we also schedule at some point? So for instance, for example, for you, when would be good time to do that?
So I'm in Europe. So right now, morning your time is good. Late afternoon is not very good because it's very late on my side. But morning sessions are fine, and I can make time all this week.
How about tomorrow morning? Is it?
Yeah.
Good for, okay. 10:30. What's the most natural starting time here?
It's any of the two is fine. Just let me know.
Whatever people are happy with, 10, we were starting at 10 last week.
Okay, let's do 10 tomorrow, if it's okay. Thank you so much for volunteering.
Yeah, I can try and explain what I'm using. I'm not using anything advanced, but I know how to run hundreds of experiments and keep on top of them. That's the question.
Well, the question is mostly about resource management, but I think it's whatever you have would be good start. So that's probably good.
Okay,
yeah,
so let's talk about that and yeah, I can try to help with the source I have and all that.
And what about the formal method? When is the good time for you?